It's a real honor to be able to give a lecture named after Ralph Peck. And so what I want to do before I get into my technical presentation was reflect a little bit on what Ralph Peck meant to me, the influence he had on me, and how that relates to the topic of soil liquefaction that we're going to be going through later. And so very early in my career, I had a very good fortune of being included in a consulting review board on a dam project, and had the chance to work with Ralph Peck. Now, I knew Jim Mitchell, as you understand. I was a student of his, and I knew Liam Finn, was also a student of his, and both of these gentlemen were great mentors and friends of mine ever since, and so I was very fortunate to have them. But this was my one chance to get to meet and work with Ralph Peck, and it was just an absolute pleasure, because he was a perfect gentleman and just a great model on everything I think makes us proud to be associated with him. And you know, he had a big influence on me as I was a graduate student getting into geotechnical engineering. And of course, we all read Terzaghi and Peck, and we all read Peck, Hansen, and Thornburn, and I had those back and forward. But the book that really made a difference to me was the book Judgment in Geotechnical Engineering. Now, this is a book his former students put together. It's a collection of his technical papers, kind of opinion pieces, and consulting reports. And what I really liked about this book was that it brought the field alive, it gave it a personality, and it made it exciting to go into this field. And so that stuck with me for a very long time. And you know, he didn't just talk about the technical stuff, he talked about philosophy. And one of the things he talked about was the roles of theory and empiricism. And you know, Terzaghi talked about this and others talked about it, but Peck had a way of doing it very nicely. And so the theory plays the important role of providing the means and framework in which we can interpret the world and our observations. The case histories and the field observations provide the way to ground us in reality and make sure we know what our theories do and don't do for us. And it's always the blend of the two that provides us with the way forward. And I really love that message and that philosophy. Again, as a student, really excited me getting into this field. He also took time to talk about development of people. And one of the things he often talked about was developing a sense of judgment in ourselves and the people around us. And I always thought that was also just really exciting. That judgment thing, I wanted some of that stuff. And so I get into liquefaction, and I spent the last 25 years working on this. And as I think back on it, the lessons from Ralph Peck's writings stayed with me, and I like to think they inform the way that I like to look at this, and I wanted to elaborate a little bit on that. And so I want to start with the discussion of a very simple question: what is liquefaction? I'm going to look at this both theoretically and empirically, and I'm going to do this with the parable of the 6 blind men and the elephant. Now, this parable has been used in other branches of science. It's usually when you have a very complex problem. If you come at it with one perspective, you don't get a complete enough view to really get a grasp on the whole thing. And so to be able to understand this elephant called liquefaction, you need to walk around it and get a sense of all the perspectives and the pieces of the problem. And I think that lesson applies very well to liquefaction. So if, for example, we're in the lab, we can very precisely measure pore water pressure ratios and shear strains. But if we're doing centrifuge models, it's a little more complicated. We see diffusion and we see localizations, more complex processes. You go out in the field and you don't see any of that. You see cracks, boils, and spreads, the manifestations. If you're worried about stability, you see flows or not flows. And if you're numerically simulating it, you worry about things like loss of uniqueness. Or maybe you just want a simple analog like a sliding block solution. Now, each one of these perspectives gives you a valuable view on the problem, and they each give us something that's very helpful for us in dealing with liquefaction. But each one on their own is insufficient to really get a handle on the problem of liquefaction. And I think that earlier message about the blend of theory and empiricism applies very much to liquefaction. We may individually be experts in one or two or more of these areas, but to really get a perspective on this problem of liquefaction, you need to take the time to walk around the different perspectives and get a fuller view. In any branch of science, you make advances by having a theory that explains all your observations, not the observations from one view, and the same thing applies to liquefaction. So now, Peck also wrote about development of people. And in his Lawrence Birham lecture, he talked about where has all the judgment gone. And in that paper, he argued that we need to aim at consciously fostering judgment in ourselves and the people around us. And what is judgment? Well, judgment is the ability for us to make good decisions. And good decisions, taking into consideration all the things we know or don't really know. And in making those decisions, what you find when you work on liquefaction projects is that the path to a good decision can come from any part of the problem involved in either assessing it or remediating or dealing with it. So you don't necessarily know where that good judgment or good decision is going to come from. On many projects I've worked on, it's been controlled by a knowledge of a geologic detail or some aspect of depositional processes. Other times it's driven by an understanding of limitations in our in situ testing or lab testing capabilities. It might be driven by an insight on how case histories tell us and what physical models tell us about certain behaviors. Or it might be driven by our understanding of insights that we get from doing numerical analyses. Sometimes it's driven by an understanding of design and construction and knowing what we can reasonably and practically build. And other times it's driven by an understanding of what can we do that is most effective at reducing risk to our people and our society. And the path to a good decision requires a familiarity with all pieces of this puzzle, this big elephant called liquefaction. And so I think the advice in Peck's writings about trying to foster judgment, I guess to me what that means is we may have expertise in individual areas, but the path towards good decisions is taking the time to walk around the problem and have at least a working familiarity with all the pieces, understand how they come together, have a context for knowing where you fit, and then together as a team being able to deal with these problems. And so for me, when I think back on the writings of Ralph Peck, in particular in judgment and geotechnical engineering, that was what excited me as a student, and it stuck with me. And I'd like to suggest that anyone new to this field, any students, get a copy of Judgment and Geotechnical Engineering, have a read and see if it does anything for you. It certainly did for me. So that is my preamble. And now I want to switch, and I want to talk about liquefaction, and I want to talk about the role that spatial variability plays and how we deal with it. I'm going to ask a very simple question to get into this. And the question is, how does spatial variability affect the way that liquefaction manifests itself in the field? And how should we select the properties that we're going to use in our analysis models, given that most of those analysis models are going to assume uniform properties in different strata? So how do we get those properties? And a way to get some insight on that, to be able to have a little better judgment of how we do this, is to use some nonlinear deformation analyses. That will be abbreviated NDAs throughout the rest of the slides. We're going to pick 4 different problems, and we're going to do the analyses using spatially variable sets of properties or stochastic properties. And then we're going to turn around and repeat those analyses with uniform properties. We're going to compare the two, and we're going to try to emphasize kind of what insights we can pull out of it, again, trying to foster that sense of judgment. So with that question, the outline kind of goes like this. I'm going to take a couple more minutes on motivation and some background. We're going to do nonlinear analysis, so I'm going to introduce the constitutive model that we're going to use. Then I'm going to describe 4 sites, 3 involving spatially variable sand deposits. First will be a case history, the other 2 will be general problems. And then I'll do a 4th one, will be interlayered sand and clay deposits, which will be the case history of Cark Canal, and then we'll try wrapping it all up. Now, you can never do any of this stuff without good friends and colleagues, and so everything I'm going to show you builds on work that I've done with the following people. This includes Ed Idris, Katerina Ziotopoulou, Jack Montgomery, Sean Munter, Chris Croggy, and Jason DeYoung. So with that, let's go back to our motivation on this. I'm going to do an easy one for us to get started. We're all familiar with triggering correlations. So this is Idris and my recent CPT-based triggering correlation. I think this embodies some of the things that I was saying about Peck's writings, and that is you have, in building this correlation, you have a theoretical framework which provides the basis for you to collect and interpret the case histories. The case histories provide the ability for you to constrain your relationship, but on top of it, there's a heaping of judgment. And the judgment are all the other things that constrain correlations where you don't have the same amount of data. How do you build things all together? And then the second thing is, how do you reduce a case history to an individual point on a plot like this? And that is an element of judgment, which is often asked, how do you do that? So I figured that'd be a good topic. Now I'm going to put in the wildlife liquefaction array. We'll do it in more detail later, but just to start, at this site, it was this layer, this stratum of sandy silt and silty sands, which liquefied in the 1987 Superstition Hills earthquake. And if you look at the CPT tip resistances in this profile, they range from lows of about 20 to values that are more than about 140 atmospheres or tons per square foot. So it's a pretty big range. And how do you represent a case history like that in a correlation? Well, the way we looked at it is we realized that in order to get movements and damage, you have to trigger liquefaction at least a good portion of it. We don't really know how much of it, but a good portion of it. The most stable way to kind of describe the strata, however, is to look at mean values, so that if we have a limited number of borings, it's a more stable estimate or characteristic of the stratum. So we take all the CPTs in that profile, we put them together, and we plot it as a single point, which is this mean value, which is essentially the same as the median, at about 121 after you do the overburden, stress, and fines corrections. That's an element of judgment. And that's the thing that we've been wanting to go back and just have a closer look at, how that influences everything we do. So, if we got the spatial variability, how are we going to deal with it? Yeah, there we go. There's one way to deal with it is to, well, that looks weird. But anyway, spatial variability, you can do it explicitly. You can incorporate using stochastic simulation models, and others have done that for different kinds of situations. Or more commonly, what we're doing is implicitly picking a number, a representative property, which we're going to use to account for that variability. And when we mean representative, I'm referring to the value that you'd use so that your uniform analysis model approximates the mean response that you would have gotten from a set of stochastic models. So when I refer to representative model, that's what I'm after. Now, representative properties have been looked at for other kinds of problems and applications, and anytime you do this, there's three things you need to consider. One is the scale over which the properties fluctuate. The second is the scale of the structure or the deformation mechanism. And basically, if you can think, if I have a large failure mechanism, it's larger than the scale over which properties fluctuate, you get more averaging of properties. And so that becomes very important in how you pick these properties. The other thing is the mechanism of deformation matters. So depending on what kind of problem you're looking at, you need to examine it specifically for your problem. In our case, it's going to be cyclic mobility and liquefaction, reconsolidation strains, and things like that. Okay, so if we want to look at this problem, one part of it is going to be understanding the scales of fluctuation in properties. Now, seldom will we have enough penetration or cone penetration test data or in situ data to really define that statistically, and so we have to use be informed by understanding of the geology and the depositional processes where we can put bounds on it. So if you know you're in a meandering stream, such as in this upper left, you can see that there's very short distances, you get big changes in properties, and other times strata are much more persistent over larger distances. And you can get at that by understanding the depositional environment. Okay, well, with that said, now I'm going to go on to the analyses. Probably the set of papers that is most applicable to what we're going to look at today and what we're building on is the work by Popescu and Prevost and others. In a series of papers, they did both two-dimensional and three-dimensional dynamic analyses using stochastic models. They were looking at level ground sites, and they did it with and without structures. From those analyses, they concluded that if you wanted to get the maximum pore water pressure at your site, you would be best able to get that using the 20th percentile property in your uniform analysis model. So keep that 20th percentile property in mind. Now, others have looked at spatial variability using other techniques, often combined with 1D analyses of local indices of displacement. But for our purposes, the work by Popescu and Prevost is most directly applicable. Okay, now what do we do in practice? Well, Perlier and Beatty gave a nice summary of what's common in US dam engineering practice. And what you find is it's fairly common for people to use a 33rd percentile property when you're defining the properties of an individual stratum. And we'd use that for both the triggering and the residual strength analysis. Now, sometimes people will push that number up to the 50th percentile when they're doing the residual strength or post-shaking stability analysis. So now we've got numbers that go 20th percentile or the 33rd to 50th percentile, and we've got a bit of a range to think about. Now, I would point out that the numbers we're using, As far as I can tell, there's no formal basis for them. It's an element of judgment passed on down from consulting review board to review board. And it seems to be a pretty reasonable judgment, but it's nice to go back and look at these things a little more quantitatively. Hence, today's question. So what we're going to try to do is look at the role that spatial variability has in how liquefaction manifests itself, and then we'll go and look at how do we pick properties for analysis with uniform analysis models. So that's the plan. Okay, so with that background, we're going to move towards doing some analyses. We're going to be doing them nonlinear, so I've got to introduce our constitutive model. It's a plasticity model for sand, hence the acronym PM for sand. Now this is going to be all work with Katerina Ziotopoulou. Am I getting the accent right? Yeah, I'm getting it right. Yeah, okay. It's only been 5 years of practice. Okay, so our constitutive model is a critical state stress ratio based bounding surface plasticity model. And we start with the model by Defalius and Manzari, and then we started modifying it. And we made quite a number of modifications, but they're all designed to make the model behave better for applications to earthquake engineering. After we had the model all together, we then provided generalized calibration so that it's easy to use. That's our goal. There's all set to run in the program FLAC. We have several versions. The most recent version, version 3, we just posted last year. You can get a copy of our manual, the dynamic link library, and example files off my website. Play with it. By all means, please let us know your experiences. We really like to hear how it works out for everyone. Okay, so I'm not going to do any equations. What I do want to do is talk about the philosophy of how these models can be used. And so in our model, we give you 3 primary parameters. These are the ones most users are going to use. The first is going to be the relative density. You'll get that based on some estimate using SPT or CPT data. The second is going to be the shear modulus coefficient. This sets the small strain modulus G max, and so you're going to get that by calibrating it to your shear wave velocity data. After you have all the other parameters set, the third parameter is the contraction rate parameter that you use to calibrate the model, so that in a single element simulation, your model gives you the cyclic strength, that cyclic resistance ratio that you want the model to give you, and you're going to base that on your SPT, CPT, or shear wave velocity based correlation for what strength do you want, and you make the constitutive model give you the property that you want. So that's how you calibrate it. Okay, so there's a few more parameters, right? There's 18. That's more than I saw in an earlier quote. So the way we go at these secondary parameters is view them as a good thing. These are the things that give you functionality. And we use these parameters. We're going to set them by calibrating them to a set of design correlations and typical responses that we think are reasonable that we would use if all we knew was an SPT or CPT penetration resistance. Now, if you have lab data, you can calibrate any of them if you want, like we do if we're doing centrifuge studies. But most times, you won't have lab data, and you're going to want to stick with the default values that we give you. Okay, so 18 parameters, and the common question is, so how do you get all those parameters? Where could you ever get those things? And I think I want to change that question. The question is one of functionality versus simplicity. This is a picture of my first car. It is a Volkswagen Bug. It is simple. It is easy to understand. It was not particularly safe. It was a lousy car to drive, and it had no heater, and I lived up north. So this was not a good car, but it was simple. This is a picture of my new car. I like this car. I open the hood. I can't understand a thing under it. I can't work on it, but it rides really nice. It's safe, and it's comfortable, right? And why is that? It's because it's complicated. Somebody worked under the hood, put in a lot of complications to give me functionality. And by doing that, they set all the timing and all the other things that make this car ride reliably and smoothly. And that's what you want in a constitutive model. There's nothing wrong with complexity. You just want it to be easy to drive. And that's what we're trying to do. A car has a gas, a brake, a steering wheel. We give you a relative density of G naught and an HP naught. Okay. So now you want to know how you drive this thing. So when you drive a car, you want to see how it performs, right? So what we're going to do is we walk through a series of single element simulations so you can see how the model performs relative to the behaviors that you think are reasonable. So these are all going to be simulations. This shows a stress-strain response with the equivalent G over G max and equivalent damping ratio behaviors. And those are then compared to correlations that we would typically use, and you can see that they capture it pretty well, and they get the dependence on overburden stress pretty well, so it behaves well. You just have to be okay with that kind of car. We also want it to behave well for cyclic mobility. So for example, this is a stress-strain response for a 35% relative density. I want it to generate lots of strain per cycle after it triggers. And then for something that's 55%, I want it to generate less strain per cycle, and so on and so forth. So we calibrate the model so it drives well for you. If you're going to be doing short duration, long duration earthquakes, it's going to be important that you get the slope of the cyclic strength versus number of cycles to trigger liquefaction. You need to get that about right. So our model gives us about the right slope. It gives us a reasonable dependence on vertical overburden stress so that we approximate the K-sigma relationships which we think are reasonable to use in application. We're also worried about slopes, and so our model, look here at the cyclic strength versus initial static shear stress, which is just a measure of slope angle, or the stresses that come within a slope. And what you want is it to track like lab data. So if you have a loose sand, you want cyclic strength to go down as the slope gets steeper. If you're a dense sand, you want the cyclic strength to go up as the slope gets steeper, and you want them to naturally rotate to the right as you increase overburden stress. And so these are the things you want your model to do, and you want someone else to do that work so it's easy to drive. Now, all cars come with manual. Most people never read a manual, and that's why you see people not knowing how to set their clock radio 6 years later, right? I'd suggest you read the manual. And in the manual, we show responses for a range of relative densities, a range of overburden stresses. We show you responses drained, undrained, monotonic, cyclic, and post-cyclic. And the reason is we want you to see how the model behaves. We want you to know when it does things reasonably well, and we want you to know when it doesn't. Because as a user, you should know the limitations of a model and what it can't and can't do. And this is open advertising, or fair advertising, so that you can look and see, is it the appropriate model for use on your problems? So with that introduction to our car, we'll now go on to 4 different problems. The first one I want to look at is the wildlife liquefaction array and its responses in 1987. This one and the next 2 things we're going to go through all work with Jack Montgomery. And so if we look at the liquefaction array, it's along a meandering segment of the Alamo River. It's about 23 meters away from the river bank. And you see the boil that Tom Holzer took a picture of after the 1987 earthquake. And there's the strong motion station in the background. So we know we've got liquefaction. The problem strata is this layer of sandy silt to silty sand between about 2 and 7 meters depths. We have a seismometer. In the stiff clays underneath it, we have a seismometer at the surface, and then we'll also take a look at this response of this piezometer P5, which is near the top of the layer. Now the goal here is we're going to try to go through a set of analyses just to see if the model does reasonable things. We want to see if our model is at least consistent with the observations, at least to the first order. So our model is going to be pretty simple. It's an infinite slope problem. This river channel is a little farther away. We have stiff clay on the bottom, clay crust on top, both assigned the median strengths based on the CPT data in the profiles. And then what we're going to do is input stochastic fields for the properties of the sand layer. And those stochastic fields are going to be spatially correlated random fields of CPT, QC1, clean sand values. So what that means is that in every element in the sand layer, gets assigned one value of QC1N, clean sand. For that value of cone tip resistance, the model is then calibrated to the triggering correlation by myself and Ed Idris, and that defines the calibration. Oh, and we used the shear modulus correlation of Stokey and Andrews. And so that fully defines how we calibrate the model. You look at this figure, the green is about the median condition, red are loose, blue are dense. You're using an anisotropic field, so you can put in you get that lenticular structure. And then we have a range of different realizations that we're exploring to see how much this mattered. And I think what I found interesting is putting in some stochastic variability is most of the battle, and then it's less sensitive to how you did it, as long as you're within reason. So the first order is just to get something in there. This is the response of one of those realizations. In the top is the acceleration at the ground surface. The black line is the recording. The red is the simulation result. You look in the time history, somewhere around 15 seconds, you can see that the motion starts to elongate in its period, and you get this softening in the response. You can see later out in time these spikes and accelerations. Those are well recognized as being due to when the sand goes through phase transformation and stiffens as part of its cyclic mobility response. And you can see that the model is doing reasonably well in approximating that response. Now below it are response spectra for, this time, a set of simulations. So this is a set of 7 different simulations, all in red, and you can see that they're not that different. So even with a broad range of different spatially variable properties, the responses were pretty consistent. So we felt not too bad about that. So let's go look at pore pressures. There were some problems with the pore water pressure recordings, which are well described in the literature. So in the top figure, you see the response of 4 piezometers. And when you look at these piezometers in time, you see some show very little dynamic response during shaking. And the absence of dynamic response suggested that they may not be saturated, as further investigated by Ron Scott and Hushman. Now, keeping that in mind, if you take allow into various drift corrections, baseline corrections, and other things that were done, you end up with these piezometers down here, the corrected results. And the blue one, P5, is the one that was believed to be the most reliable. And you see that it hits about 85% pore water pressure at about the end of strong shaking, and then it slowly rises in time. So keep that in mind. We want to see, how does that work? So this is the response of one simulation. In the top plot is the excess pore water pressure in time. There's a bunch of red lines, because what we're doing is we're looking at a series of points that fall at the elevation of piezometer P5, but they're just at different locations. So some are in dense pockets and some are in looser pockets. The looser pockets build pore pressure more quickly, the denser pockets more slowly. Depending on what you set the permeability or hydraulic conductivity at, then these two will come together with higher permeabilities, that they'll collapse together or they'll stay apart. And you see a progressive rise over time for some of them as pore pressures diffuse from the looser zones into the denser zones. And I think that's just an interesting observation that contributes to trying to figure out what was going on at that site. So that is interesting. If you then instead look at deformations, now the lateral spreading at the site is estimated to be about a foot, 30 centimeters. So here's the lateral displacement from our model in time. You see right about 15 seconds, we start to see movements. Maybe around 20, we start to pick up more significantly. If you look at those displacements, they get to about 12 centimeters. But we used a ½ a degree slope. If we put a 1 degree slope in, we get over 30 centimeters. So this is in the slop of the analysis, right? Then if you look in the bottom, we're plotting the percent of the layer that triggered liquefaction. And the red line shows that at about 20 seconds onward, we have about 20% to 35% of the stratum has triggered essentially 100% pore pressure ratio. A larger chunk of the layer has gotten up over 70%, but the movements onset start when you're somewhere between 20 and 35%. For this realization. So we have a bunch of other realizations, and that number's generally between the 20th and the 50th, depending on the details. So to kind of wrap up that wildlife site, we ran these nonlinear analyses using stochastic realizations for the properties, and we kind of conclude that we got responses that are in pretty reasonable agreement with what we observed. The responses show that the site softened and ground deformations accumulate after about 20 to 50% of that silty sand and sandy silt stratum essentially developed 100% pore pressure ratio. We also saw that detail, that diffusion of pore pressures from denser to looser zones can affect that slower migration of pore water pressures. And this is something that, for example, was anticipated in a discussion of it by El Khatib and Peter Robertson and others. And so this was just to quantify that, in fact, simulations will track that. Now, there are long period ground oscillations that happen after strong shaking, and we are not getting those. Now, we're underestimating them, and that very well could be because we're not getting the impact of the surface waves, which is a detail that Tom Holzer and Les Yaud pointed out. Now, that said, the model does not bad, and you can't expect it to give you everything. The purpose of the model is to get some insights into the behavior, and in this sense, we felt that this was encouraging. Let's go look at what other things can tell us. This brings us to the second problem. In this one, we're going to parameterize the first problem and see what else matters. So this is looking at an infinite slope geometry It's just the same as what we did before, but now we're going to parameterize properties, densities, ground motions, and other things. So we'll change the thickness of the sand layer, thickness of the crust, length of the mesh, et cetera, et cetera. This is just one realization to illustrate the idea. So in this time, all the properties are cast in terms of N160 clean sand values. I don't know why the difference, we just did. And then it's all calibrated to the triggering correlation by Idris and myself. And again, if you look at this realization, it has the lenticular structure. Green is about the median. This is a realization where the mean value is a blow count of 15. Coefficient of variation is 40%. The individual blow counts are the blue dots, and they go from as low as 1 to 30, where the average at any one elevation is about 15, which it should be. And you look at the plot, the red are the loose lenses, and the blue are the denser lenses, and then we can generate various cases and look at what it's sensitive to. Now, I would point out in all cases, the mesh is longer than the scale over which the fluctuations are. And that'll come up later as a kind of a limitation of the scope of conditions we looked at. Okay, so you take all the SPT blow counts assigned to all the elements, you rank order them, and you get a cumulative distribution. So the red lines are the cumulative distributions for 50 different realizations with the same set of properties. And if you look at it, the 50th percentile is the median value of about 15, which is what you'd expect. So we'll run dynamic analyses with all these stochastic models, and then we'll run uniform analysis models using different equivalent percentiles. So for example, we'll do the 20th percentile, which is a blow count of 10, et cetera, for different uniform percentiles. Okay, now here's the first complicated figure. So I'm going to start over here on the left figure. This is the maximum lateral displacement that we get versus peak ground acceleration, where we're feeding it in one ground motion, 50 realizations. At 0.2 Gs, you see the red diamonds. The red diamonds are all the stochastic realizations. And the first thing to note is that from low to high, it's about a factor 2 variation. And that variation just represents the contribution of spatial variability to uncertainty in our ability to predict deformations. So you never get away from that. The red line is just connecting the median results for all the stochastic realizations. And there's a high confidence in the line because we have so many realizations. Also shown on the figure are the black dashed lines. The black dashed lines are all for uniform analysis models where they're run for some uniform percentile. And so if you come down here, the median result of the stochastic is about equal to what you'd get with a uniform model at the 50th percentile property. That's where we start. Okay, now, I would note that at this point, we're at relatively modest deformations, like maybe 20, 30 centimeters, kind of like what we saw at wildlife. Now let's shake it harder. If you shake it harder, you get more displacement. As you get more displacement, you get a better prediction if you're using something closer to the 70th percentile. Now, why is that? That's because in order for that sand layer to move laterally, you have to strain everything. Not just the looser pockets, but you've got to strain the denser pockets too. And the denser pockets are disproportionately strong relative to the looser pockets, and they act to buttress the movements, so the denser pockets are starting to have a bigger influence on behavior. So we see this pattern over and over again, depending on the magnitude of the strains induced in the layer. Let's switch and look on the right side. This is the maximum reconsolidation settlement anywhere along the surface of the ground of the model. If we start here at 0.2 Gs, you see that you would now get the median settlement with about the 30th percentile property. And it's about the 30th percentile because if you have a loose pocket right underneath a crust anywhere along the slope, it liquefies, it settles, and you get the maximum settlement over the loose pocket. And so it's the pockets that can control the maximum settlement that you get at the site, not some average property. Then, as you shake it harder, you trigger liquefaction in more and more of the stratum, you get more and more averaging response, and we grow up closer to the 50th percentile. So this magic uniform representative percentile isn't just a single number. It's going to depend on things. There's another detail which I think is fascinating that comes out of these results. And let's start with the top figure. This is the settlement of the ground surface versus position along the slope. Now, we've only got 7 realizations on there, or there'd be too many red lines. They illustrate what happens. You see these red lines are warping because the crust is only 1.5 meters thick. And so what's happening here is you have a loose pocket and it tries to strain a lot. it's up against the dense pocket, which doesn't want to strain, and that incompatibility of movement warps the ground surface. And the warping of the ground surface causes more differential distortion than the actual reconsolidation settlement does. And this is exactly what we see when we go out and look at sites like in Christchurch or Tohoku or other places, thin crusts and shallow water tables. If you make the crust thicker, like 3 or 6 meters, that thicker crust suppresses the warping. You get a lot more uniform settlement and a lot less distortion going into our structure. So crust thickness matters. And you can't get that detail with uniform analysis models. Okay, so now that's it. Now I'm going to do ground motions. This is a little harder to illustrate, but what I'm going to do is I'm going to just take a subset of 7 realizations, 7 motions. The 7 motions scaled to 3 different PGAs. And on the left, we're going to plot the maximum lateral displacement of the model versus now the cumulative absolute velocity, CAV5, which correlates better to the displacements as Steve Kramer and his colleagues have shown. So if we look at this figure, let me start here. There are 3 symbols. The first symbol, the gold square, is the uniform analysis model, the 20th percentile property. The circle is with the 50th percentile property. And then in between the red hatched zone is the 7 realizations, all for that particular ground motion. And it's just hatched because otherwise there's just a bunch of points. It makes it hard to see. And all those realizations fall between the 20th and the 50th percentile in this side of the plot. So on the other side, we're plotting the equivalent uniform percentile that you would need for each individual stochastic model to get the same displacement versus CAV5, and that is why these 7 points all plot between the 20th and the 50th percentile. That's at low shaking levels. If we shake it harder, we're up here, and the red hatched zone is in between now the 50th and 80th percentile, which is why over here they're between the 50th and the 80th percentile. So with that introduction, when you're looking at the right-hand figure, going down kind of the middle of the road, you'd see that the equivalent uniform percentile across these different ground motions and realizations would be about the 30th percentile. And as you shake it harder and get more movement, it increases up to, say, the 60th or 70th percentile. So you get that dependence on displacements. These 2 figures say the same thing. The top one is if the median blow count is instead 7.5, so a very loose condition, and you see the uniform percentile you might use would be, say, the 50th percentile to maybe the 70th or a bit more. The bottom figure is if it's very dense, so we get a median blow count of 30. In this case, our representative percentile is somewhere down near 30 to 40%. So now it depends on densities. So if we kind of pull all those together, those parametric analyses and a few others, which, by the way, are all limited to the case of cyclic mobility. We're not looking at flow deformations. And they're all the case where the deformation zone is larger than the scale of fluctuation, so we're getting some averaging. That in those cases, let's talk about settlement first. And you look at settlement, the stochastic model illustrates that a relatively thick crust can reduce differential surface settlements, whereas a thin crust can warp and be worse than otherwise. That if you ran a uniform analysis model and you used a 33rd percentile property, well, you would get a reasonable approximation of the median post-liquefaction reconsolidation settlements, but you'd be missing 3 important things. And the 3 important things are recognizing that most constitutive models cannot estimate post-liquefaction reconsolidation strains at all. And the reason is they're not built to do sedimentation strains. Now, we're doing it because we have a kind of a heuristic patch on it for the post-shaking modeling of it, so it does better. But this is something you should know most models don't naturally do. The second thing is that a uniform model will never tell you about that distortion that comes with thin layers, so you'll underestimate the ground distortion in those cases. And the third is that none of our models model the loss of ground due to ejecta, and you've all seen the photos of Christchurch and Tohoku. The amount of sand that came up contributed a lot to settlements, and no model is going to give you that, at least at this point in time. If we talk about the lateral spreading part, a representative penetration resistance to use in a uniform model, well, it's generally between about the 30th and 70th percentile, depending on a bunch of things. The representative value would be closer to the 33rd, or that lower end, that 33rd being common in practice, whenever we have thicker liquefiable layers, thicker crusts, steeper slopes, denser soils, and smaller levels of deformations. But it's a little hard to say that we're comfortable saying exactly when you're going to get it. So you're somewhere in that range. Now I'll come back to a bit of that later. The next thing, though, I want to do is switch to a slightly different geometry, and that is we're going to look at an embankment dam to see if any of this holds up. So the dam we're going to model is 45 meters high. It's on a 12-meter thick alluvium layer. The shells are going to be a compacted gravelly sand modeled with PM4 sand with a blow count of 35, so it will not trigger liquefaction. The core is given properties consistent with a compacted clay core circa, say, 1970s in California. And what we're really looking at is the alluvium, and we're going to be looking at its spatially variable properties. This is one of those realizations for the properties in the foundation. The little black dots are all the individual blow counts. Again, they go from 1 to 30 because we're using a mean N160 clean sand to 15 and a coefficient of variation of 40%. The average blow count at any one elevation or position along the slope are the cyan dots, and they're about 15. And you look at the figure, you see the greens are about close to the middle, the red is loose, the blue is dense, and we're getting that lenticular structure, that rafter. And then we can vary that and look at things. If you rank order all the blow counts assigned to the elements in the foundation, you get the blue cumulative distributions. So there the median value is in fact at about blow count of 15. And then again, we'll run uniform analysis models as well, using these different equivalent percentiles, like 20th percentile being blow count of 10, et cetera, et cetera. So this is the first comparison. This is a contour of shear strains. In the upper figure is for a realization. This realization, if you look at the strains, the dark blues are the higher shear strains, and the strains are concentrating in the looser zones. And so the way this thing deforms is you get shear strains concentrating in the looser zones, stepping over from one loose lens down to another loose lens, up to another loose lens. And so you get this coalescing of strains across the looser pockets. When you look at the lower figure, it's a uniform model, and you don't get that same concentration of shear strains. So now let's look at some things that we would be particularly interested in. The first one on the left is we're going to look at settlements. So this will be the crest settlement and versus PGA. This is going to be for one ground motion. And then on the other side will be the horizontal stretch. Horizontal stretch is the sum of how much the upstream face moves in the upstream direction and how much the downstream moved in the downstream direction, just as a measure of how this thing deforms laterally. So start on the left at the low shaking about 0.4 Gs. This is all for one motion. You see now the purple triangles or diamonds, there are realizations, and you see that these 7 realizations have a much narrower range of response. And that's because the deformation isn't just dependent on the liquefiable soil, but it depends on the strength and properties of the shells and the core, and so you get a little bit less sensitivity to the sand properties. The median result is the cyan value. The black dashed lines are again the uniform models with these different uniform percentiles. In this case, that would correspond to, at the lower end on the left, would be about the 30th percentile would be a good agreement. And as we shake it harder and get more displacement, it again increases, and now we're up closer to, say, the 45th percentile. If we look at stretch, it's the same thing. Smaller movements, the equivalent percentile will be about the 34th, and then it increases closer to maybe the 50th, always increasing as we go to larger demands on the layers. Now, we can vary that. We looked also at loose sand, we looked at dense sand, we looked at different motions, and that pattern shows up over and over again. I threw in this one because it's a little different. It's when we change the layer thickness to being only 3 meters thick, and when it's only 3 meters thick, then what happens is when it tries to deform, it can't go from loose lens to loose lens. It's got to go through everything in that elevation. So you hit all the dense pockets and the loose and the dense and the loose. And as a result, the deformations don't look terribly different than with a uniform model. So if we look at the same set of figures, over here on the left, the settlements, you would get that cyan dot, that median result with about the 50 to 60th percentile right across the board, 50th to about 60th percentile. We're getting more averaging. Again, with the denser pockets having disproportionately greater resistance than the looser ones. And then you go to the stretch, again, we're kind of around that 50th percentile. So the pattern actually holds up pretty well with what we saw before. So from those parameter studies and others, what we see is results consistent with those for lateral spreading, as long as you look for the trends relative to overburden stress, steepness of the slope, and the thickness of the layers. Again, everything's for cyclic mobility. We're not yet into flow deformations. And again, everything is limited to the case where the zone of deformation is several times greater than the scale of fluctuation, so we are getting some averaging effects. So with those caveats, if we were doing deterministic analyses today, we have to pick a representative property to put into a uniform analysis model. That 33rd percentile, which was an element of judgment, seemed to have been a pretty reasonable number. It's on the lower range of what we see, so it's reasonable to reasonably conservative. It's not a bad place to be. Maybe we'll do better as time goes on, but that's not a bad judgment in the end. If we're doing stochastic or a probabilistic or risk analyses, it's possible that you might consider looking at a range of percentiles to see if the problem's sensitive to it, if you think it's warranted. I think, though, that in time, if it turns out to be important on a project, it won't be hard for us to start running sets of realizations that are conditional on our borings in the same way we run sets of ground motions. So just run a set of 7 realizations and 7 motions and get a sense for how much variability is hurting you at a site. It gives you a venue, a way to demonstrate the utility of adding borings, because you'd be able to show, does it in fact reduce your uncertainty? And that's a good way to structure problems. So that's the third one done. Those were all spatially variable sands, and we're now going to switch, and we're going to do a different one. This time we're going to look at interlayered sands and clays. And this work is all by Sean Munter, Chris Croggy, working with me and Jason DeYoung at UC Davis. So this one we're going to look at a case history again. It's the Cark Canal from the 1999 Kojeli earthquake, a magnitude 7.5 earthquake. This is all described in the paper by Les Xiao, John Bray, and others in the journal in 2009. And what they reported was the absence of visible damage or deformation, so nothing happened, they can see, despite an estimated PGA of 0.4 Gs in a magnitude 7.5 earthquake. So why not? So they looked in the area, they saw that several buildings had settled about 4 inches. This suggested there were zones of liquefaction or cyclic softening, but they didn't see boils and it wasn't producing large movements or cracks near the channel. So they go back and they do some investigation. So if you look down here, these are a bunch of CPTs that they push at the site. There was 5 total. And you look in these CPTs that at this elevation, this is primarily an interbedded fine-grained sediment deposit. But in this interbedded fine-grained sediment deposit, mostly clays, you see sand seams. So these little blips in the cone tip resistance are identifying a bunch of sand seams. And those sand seams, if you do a liquefaction analysis, they would all trigger. And so they did that analysis, and then they put that into a multiple linear regression model, Bartlett and Yaud, to predict how much lateral spreading. They got a lot of movement, and it therefore is not consistent with the visible absence of movement. So what could be going on? They then said, well, let's ignore the sand layers and say it's all clay. So if we analyze it, if it's all clay, you get small movements, and it agrees with what you see, so that seems to be about right, which leads to the conclusion, this is quoting from them, that at the Cark Canal and Cumhuriyet Avenue sites, the absence of lateral spread at these sites indicates that these liquefiable layers are most likely discontinuous lenses, and that the shear strength of the clay between the lenses is sufficient to prevent the lateral spreading. And that's a pretty reasonable judgment. But the question is, can you quantify it, and when are we going to be comfortable doing it in an application going forward? So that's what we want to investigate. Now, when we look at this thing, they archive their data. It's all on the peer website. So we go get their CPT data. These are the 5 cones at the site. We break these data down into the fill layer, that interbedded fine-grained and silty sand stratum, and then the underlying dense silty sands. In each of those stratums, we then take those properties and we sort and bin them. And the first thing we have to do is break them into what materials do we consider as being sand-like or liquefiable in the sense we will use those triggering correlations, versus what materials do we think are more clay-likes, where we're going to analyze them in terms of an undrained shear strength. And so there's a little bit of a challenge there because there's a lot of thin layers, transition zones, and interfaces to deal with. So depending on how you do that, you get that there's about 23 to 40% of that stratum you would call sand-like. In the sand-like soils, The median property would be somewhere between a little less than 90 or a little more than 90 in other cases, depending on how you do this binning. And in the end, we pick 90 as the property we're going to use to represent the silty sand lenses. Same thing for the clay. If you look at the median value, the end-grain strength is about 50-ish, and so we're going to use 50 as our property in the analyses I'm going to show you. So again, we're going to run these in FLAC. The input motion is an outcrop motion from Sakurai. It's a PGA is about 0.36 Gs. This is the kind of cross-section of the model down here. The channel is about 6.5 meters deep. The water table is higher to the sides of the channel than it is in the channel itself. We have fill on top in yellow. This zone in the middle is the interbedded sands and clays. The red is the clay. The yellow colors are going to be the sand lenses. And then underneath it is that dense silty sand. We'll also model that with PM4 sand, but it's very dense and it's not going to trigger or do anything. And so then again, those are the properties. 50 kPa for the clays, 90 QC1N clean sand, and 90 for all the sand lenses. Okay, so that's our model. We're going to generate a bunch of realizations. In this case, so these are 3 example realizations. We generate this. This is a 2-category model based on transition probability geostatistics, which is a set of procedures and software developed by Carly working with Graham Fogg in our hydrologic sciences group at UC Davis. And so we take their techniques and we simulate these 2-category models, and then we're going to do some parameter variations. We're going to have the proportion of the silty sands be 23% or 40%. We're going to have cases where the mean horizontal length of the sand lenses is 5 meters and 10 meters. And then we're going to do vertical mean lengths, which will be 16 and 26 centimeters. And in all cases, there's a CPT on the left bank and one on the right bank, and these realizations are all conditional on those CPT, so they honor the data right at the edge of the channel. This is one of the results. This is showing, again, 23% sand. There's the realization in the top. These are the shear strains. Now, all the silty sands trigger liquefaction, and the shear strains you can see are mapping right up to where you have the silty sand seams up above, and the clay is not straining significantly. The movements we get are towards the channel. I'm going to be showing some plots of results where, let's say the channel was 6.5 meters high. So I'm going to look at a point 6 meters back from the channel edge. So it's one height of the channel back. And you'd see over here we'd be getting about 4 centimeters. And over on the right we'd be getting maybe 6 centimeters. And so if you take those 2 numbers, those would be 2 of these green dots. So what I'm plotting here are the lateral displacements for a point 6 meters back from the channel edge. And plotting them versus the percent sand or the proportion of sand that we have in that interbedded deposit. And those various parameter cases that we've looked at are the range of dots there. Now we're going to add more dots in the future, but I could only get Sean to work so fast. Actually, it was the computer. So anyway, have these points, and then we vary them. And if you look at those data, you see these numbers down here. When you're at 3, 4, 5, 6 centimeters, you're probably in the range of displacements where you wouldn't see damage at that site, given the kind of conditions and the ground conditions, right? So those seem to be pretty reasonable for what we observe. When you get 10 centimeters or 10 or 15 centimeters, you're probably going to see ground damage and cracking. So those aren't quite consistent, but there's a number of other things that we could do to refine our analysis and model, and we'll get to that next. But at least these aren't so far away. Now, Laschiaud and colleagues had done the multiple linear regression model, and they'd gotten really large displacements. Another way we do this in practice frequently is to use the CPT data and put them into 1D index analyses like a lateral displacement index or an LPI or any of these other models. And so I'm showing results for 2 of those types of procedures. The first one is the red triangles. These are results if you take the 5 CPTs and you calculate a lateral displacement using the Zhang et al. Procedure. When you do this, this is with transitions, corrections on. If you don't account for transitions, those displacements would be through the roof. So if you do those, you get the numbers down, but they are still an order of magnitude higher than you're getting from the dynamic analyses. The blue dots are the ones using the LDI procedure in the monograph by Idris and myself, and they're just as high. They're all an order of magnitude higher than the dynamic analyses. And why is that? It's because inherent to these 1D methods is the assumption of horizontal layering so that the layers will be able to be horizontally continuous and you can deform along them. They don't account for their discontinuous nature. So to kind of wrap up the Cark Canal, I feel like these stochastic simulations, getting some reasonable accounting of that stochastic nature into the model, we see that we can produce small to moderate displacements. We're using a range of what we think are physically reasonable interpretations of the data, that the results are consistent with the lack of damage for at least some range of those parameters, and then probably overestimating for some others, but they're all significantly better than any of the kind of standard practices that assume horizontal continuity of lenses. It does support what I think is important is the judgment by Yao et al., that judgment that the shear strength from the non-liquefiable clays between the silty lenses were what was sufficient to resist the lateral deformation. And these numerical models allow us to now quantify that, look at it in more detail, and be able to maybe one day do a better job at this. So the next point is that these 1D index analyses, again, assuming horizontal layering, are going to naturally overestimate the potential for lateral movements in these types of situations. Now, that means we've got to get better at getting the continuity of these lenses, and that's going to require two things. The first is getting better at incorporating our geologic understanding of depositional processes in how we characterize deposits. So the geology is key to a lot of this. You can do a good job if you strategically place CPTs, probably at closer spacings in certain zones to get a handle on the continuity of these lenses so that your model, in your mind, of the depositional processes has a basis. So we'd like to pursue those types of strategies more frequently. Okay, so that was a journey, right? That's 4 cases. Now I'm going to wrap up. I'm going to start with just in terms of the analyses we were presenting. We're doing these nonlinear dynamic analyses using these stochastic realizations and getting some sense of the spatial variability in there. I think it's the first thing to get realistic results. We did 2 case histories, the wildlife and Cark Canal, and then we did 2 general ones, just lateral spreading and embankment dams, and we're kind of getting consistent stories across them. If we were to talk about the spatially variable sand deposits, then if you were trying to pick a representative property for these cyclic mobility problems, it's going to range between the 30th and 70th percentile, that the lower range is what we're seeing for thicker strata, higher overburden, higher median densities, and lower levels of deformation. But if you're going to do it in practice, using that 33rd would not be a bad place to be. When we're looking at the interbedded sands and clay deposits, we're seeing that liquefaction of thin, discontinuous lenses, when we're in otherwise non-liquefiable clay deposits, they're not going to cause as much deformation as we're computing using these 1D index methods that assume horizontal continuity of lenses. So this is where we're getting a lot of bias in our models relative to our observations. Okay, so then more generally, these nonlinear deformation analyses, they're fun, right? I think they give you a lot of insight into behaviors and mechanisms and failure modes that you can't get with simpler design methods. Now, I got nothing against limit equilibrium and sliding blocks, and we all use them. They have a place. They're very useful in smaller projects. They're very useful in the obvious cases. But we run into other problems where they're just not going to tell you the details of behavior that you need to make some good judgments. And so I think these models are going to be very useful, increasingly useful for us in the future. I do want to say that if you're going to use them, the validation of the constitutive model is critical, so you know what you're doing. We recommend, or I'd require, that you do single element simulations and you drive those elements through the range of loading paths that are important to your structure, with the key being that you need to know if the model does something reasonable or doesn't. You can't rely on the developer having checked their model for what you're going to use it for. This is your responsibility. I also think that in any of these analyses, details matter. And if we're going to do a better job with these in the future, in practice, we're going to need improved documentation practices. This is important for peer review. It's important for continuity of the product so other people can keep following best practices. And I think that's what's going to be important for us to advance the standard and use of these methods in the future. Running through all of this is the geology, and an understanding of our depositional processes is also going to be vital for how we implement a lot of these things, but it's also already proves vital for any time we deal with liquefaction problems. Over and over again, we find that a good understanding of depositional processes on different projects They guide how we design our exploration programs. They help us judge the continuity and extent of potentially weaker layers. They help us judge which soils belong together, which share a common distribution, how we group, how we bin, how we sort data as part of picking those representative properties. And doing this logically is important for avoiding the over-conservatism of being worried about the looser pockets. And it's important for avoiding the unconservatism of averaging out the continuous horizontal layer with everything else. So it's important to getting a good picture to the problem. And now I just want to tie it back to what Ralph Peck, what I got out of reading his book, and again, hope many of you do, and that is that you can work towards consciously fostering your judgment. And by that, I mean your ability to make good decisions. And so when we deal with liquefaction problems, that requires that we take the time to develop a familiarity with all the issues from the geology to the soil behavior, in situ testing methods, a familiarity with case histories and physical models and the lessons they give us, the numerical modeling procedures, what they can and can't do for you, an understanding of construction methods and practices so you know what is reasonably constructible, and an understanding of risk assessment so that you know how your decisions are helping reduce risk to society. And so you need at least some familiarity in there so you can put your own work in context and work in teams to make better judgments and decisions. So I got to close with one of my last points on that is, I think when I first read Peck's book, I was like, judgment, that's cool. I want some of that. And it was like an abstract concept to me. And it's not. Judgment is not something you get just because you get old. Sorry, guys. Yeah. Judgment is something that you can explain. The reasons for a good decision can be and should be articulated based on your understanding of all the facets affecting the behavior. And that's what I just found in the one experience I had working with Ralph Peck. And at the end, when it came to making a judgment, he didn't just say, well, this is my judgment. He explained his thinking through all the parts of the problem and made the case for why that was the decision to make. And I think that's something we could do better at, starting to be more routinely articulating why we decide to do what we do. So once again, I just want to thank Ed, Katarina, Jack, Sean, Chris, and Jason for helping me put all these slides together. I really couldn't have done it at all without them. I really appreciate it. We were also supported, a lot of this work was supported by California Department of Water Resources and the Division of Safety of Dams. We really appreciate their collaboration and support. And then I just want to thank you again for the opportunity to have given a lecture in the name of Ralph Peck. Really appreciate it. Thank you.